comments on the format of the final? So we have things that we haven't tested so far are formation of the linear systems, then the iterative way to solve linear systems, like Gauss-Seidel, Jacobi, and so on. Then curve fitting, so that's lecture 7. In ODEs, that's lecture 8. All of those will have a separate problem on the final. So that's 4 problems right there. And then 2 additional problems will be some sort of summary. There will be that first, the format of the test will look the same as exam 1 and exam 2. That first problem, whether you hate it or you like it, with like a bunch of smaller questions between 2 to 5 points each, that kind of tend to take a lot of energy, but you shouldn't spend too much energy on them. You should spend more on the other ones. That's kind of how you manage time questions. That's going to be there. And then the rest are the larger problems that are set. So it is comprehensive in the sense that everything could show up, but there will be more weight on the material that we haven't tested. It's not going to be much longer than the actual, it's going to be maybe 1 problem longer, really, than your exam 1 or exam 2. So in that sense, I expect you to complete. It's not going to be a 3-hour final, it's going to be a 2-hour final. Okay? So 9 till 11. You've been tested enough in this course, there's no need for 3-hour finals. You're going to have 2 hours, 9 till 11 a.m. I believe, on Thursday. And the room is that same room we squatted in for exam 2.
Oh, wait. They fixed it.
No. The one that we actually kind of found is empty, that's our final room, by the way, on Lena. Okay? Yes.
Can you repeat the 4 questions from the material, like ODE formation?
Formulation. It's not formation, it's formulation. Rock formation, problem formulation.
Yeah.
I actually made that mistake for years. It's rock formation, but problem formulation. Little details. Second one will be something like iterative methods. Curve fitting. ODEs.
So for the curve method, would you like give us it, or will we will it be like one method or whatever it's called?
It's similar to your homework, or I give you a system, solve it by an iterative method.
So it's not like
And I can ask you to program it, or I can ask you to solve by hand. Everything that we do, I could ask you to. Some of it I ask you to program, some of it I ask you to do by hand. You need to do both in order to program, so there's that.
But like, will you explain what the method is? Like, do we need to memorize stuff? Or like
That's what your third cheat sheet is about, to have the rules on how methods work. So you can add 1 more sheet of paper back and forth. So you can have 3 sheets of paper for your cheat sheet. I hope you saved the ones you had from exam 1 and exam 2. If not, rewriting them is a great review. I mean, the idea of these cheat sheets is you're going to write them down and you're not going to look at them because you've reviewed everything you need to review. But hopefully you still have some memory of how your exam 1 and 2 cheat sheets look like, so you don't have to rewrite everything and you can just quickly, you basically know the concepts, you just look at the detail of something, how do you write it down. For instance, that darn NP range and NP link space, right? The difference between the two. It's something that, you now know mentally, oh yeah, there is a difference, I should look it up, right? Yes? Okay, questions about the format of the final? Everything clear? Yeah. And again, all of the practice problems are actually from exams at some point in time, gathered. So practice problems are real. Exam 1 and 2, I typically return to students, so those float around. Finals, I don't return, but those are sampled from finals. Okay. Yes?
Will final, like the grade that we got on the final, will that be released?
Yes.
Okay.
So I will post your final, I will also post your score, right? So if you see a discrepancy, by all means, and you don't know what happened and how it happened, email me, okay? Mistakes do happen, and sometimes, I forget that I was supposed to drop something, and you name it. Okay? That said, the record that I have for your homework is the one that is online. If that's not correct, at this point, right, we have 8 days to correct everything. So I hope you corrected everything that you needed to correct.
It's most likely gonna be a 92. It's gonna be a 92 most likely.
Somewhere there, 91, 92. So I did post tentative cutoffs. Okay. Those are plus minus a point or two, what my cutoffs typically always are. They don't change a lot. I didn't see anything in exam 1 and exam 2 that would make me change them. Like you, as a class, in terms of scores, behaved in an average way. Class in fall does. So there's, right? And I have in class in fall, I have about 60 to 80 students depending on a fall semester. So there's enough statistics, if you will. Class in spring is a little smaller. And that's where things change a little more. That's all. That's just cumulative statistics. Okay? So again, if you have a question about how, I will post your final score and your final formula I'm using is the formula that is posted on syllabus. But if you have a question about how something, just email me that question. Yes, mistakes happen. So you can always double check. Okay? And there is always, even if I submit the grades to the office, there's a way to correct them. So if it's an honest mistake in calculation, it's corrected really in a simple way. Everything is automated these days. So it's not even painful. It used to be a piece of paper. It's not a paper anymore. I just go online and correct. Any other questions? Okay. All right, so let's wrap up and then finally, there was that question came a couple of times. The solutions to the practice problems will not be posted. I don't do that as a matter of practice, if you will, because then you try harder to solve them, and you also kind of team up and go and ask questions, and it's better for your own benefit. Though for the last moment study, it would be helpful to help them, but I want you to plan ahead and not the last moment. Also, what I've noticed is that these solved problems, if and when I post them, they show up on the final in some shape or form and get copied from verbatim, and I don't like that. So I want your cheat sheets to be just general problems, and I want you to work harder and ask yourself, when you have solved problems, then it's hard not to look at the solution. And I don't want you to look at the solution, because then you will try harder and actually learn better ahead of it. Even sometimes, if you don't know the problem that you looked at, sometimes you might actually figure it out on the final itself. And I've seen that happen, and that's why I'm not posting solution, because it's just like that chocolate in my office, for those of you who were in my office. I cannot tell myself not to eat it, so I gotta give it away. But it is a good idea for me not to eat it, but if it's there, I'm gonna eat it. Same thing as you and solutions. I want you to try to solve and think about all of those problems, because they are real final problems. So it's more beneficial for you if I don't post the problems. And there's Ningyu has office hours. I am traveling, so I will not be here for final, but Ningyu has office hours tomorrow, right? He says yes, he does. You have tutors, you have places to go to look for how to solve those problems and get some input. But do try to solve them yourself first. That's your test, okay? And that's going to benefit you the most. Okay. Lecturing on how to prepare for finals is over. Now let's go to the last little piece of a problem. So we have gone through a number of methods on how to solve the problem, and I'm going to quickly review Euler method because that's at the core of how we solve problems. So what we do is, these are initial value problems, so I start from a known value. I always have to have initial value for these type of problems, whether I'm solving analytically or numerically. I got to start from something. Okay, I got to anchor it. And I start from that value. Let's say that for xi, I know what my y of xi is, which I also refer to as yi. Okay, so that's the point I'm starting from. The way I extrapolate from them on, my problem is formulated as dy dx, slope at that point, is equal to some function of both x and y. And when that function of x and y is complicated, I cannot recover analytical solution. Again, even in the cases that you can, I'm not going to really test you on how you've done in your ODE class, though I should. Okay? So I'm going to leave that be. I'm going to ask you to solve this numerically. So my problem tells me that the slope dy dx is given by this f of xy, so I can program that. I can know what that is for given x and y. So I'm going to just take that slope. In Euler's method, all I'm doing is just taking slope, okay, to be f of xi yi, okay? So I'm going to get my next yi plus 1 predicted value, okay, right here, by taking that slope for some step size h. And if we look at it long enough, you will recognize the form of it, since this is dy dx, and this is y I plus some value at xi plus h, right? This is essentially truncated Taylor's formula. Okay? So I just chopped off all the higher order terms and I kept the first linear ones. And that's the simplest method. There's some true value here that you're trying to recover, but you're going to have some error here at this step because of the truncation in this formula. Okay? So you truncated all of the higher order terms. That's where your error comes from at this step. Now, at the next step, you're going to start from this point and keep doing the same. So at this next step, you're going to have built-in error from before. So there's both history in this marching through and the error that you're making, truncation error that you're making at that time, plus the standard round of errors when you're solving this in computers. So that's all the error that shows up in this problem. Now, for all other methods, yes?
What is the error tolerance? You like go from one point to the other, but you use the truncated value.
That's truncation error. So I truncated my Taylor series, right? That's truncation error, yes. But then you also have propagation from before. That's what I refer to history.
History error?
Yeah, because basically you just propagate. The moment you make an error, that error will propagate for all of the steps forward, right? And in that step, you're also making literally a truncation error at that very moment. So sum of the two will give you the... And then there's always round off, okay? So all of the other methods are just smarter in the way they pick this slope and they tailor it they tailor it to Taylor's formula, literally. We're not going to go into how we tailor those, okay? Just know that all of the methods that are given in this table, and there's a large table that I showed at the end of last class. These are second order Runge-Kutta methods. They're just different in the way they formulate this slope. And slope is typically, I have some intermediate slopes at some intermediate points, okay? And I combine them in a weighted sum. That's essentially how all of these methods work. And programming it is relatively straightforward, assuming you're not making any typos, per usual, right? Typos take 90% of time to find. So the best one, Runge-Kutta, so-called fourth order, and fourth order because it cancels a whole lot of terms for the in-Taylor's formula, so it's actually very accurate, is fourth order Runge-Kutta. I actually take 4 of the slopes at these intermediate points, and I combine them, and that gives me very good accuracy. And again, it's not magic, it's actually calculated, we're just not busy calculating it. Okay, so now, let's say, so we can do third order, second order, like typically I'm gonna give you the formula, we're not busy coming up with the methods here. Okay? And then the programming is relatively straightforward. So when we actually programmed, for instance, Euler's, which is so-called first order method, the error is order of h, whereas the error in Runge-Kutta is order of h to the 4. So as h gets smaller, Runge-Kutta method declines much more rapidly, h to the 4 as opposed to h. Right? That's why it's so accurate. So basically when we compare the two, you can actually see that if I plot it against an analytical solution, Runge-Kutta really like falls right on top of it as far as plotting goes. Okay. So the difference is here for h is 0.5, it's on the order of 0.5 to the 4, right? Which is much smaller than order of 0.5, which here we have order of 0.5, right? That's this O of h versus O of h to the 4. For small h, it's a huge difference. So that is first order versus fourth order method. Now, fourth order method is more expensive to compute, so you will typically reserve it for problems where you really, really need accuracy, and where having this much of an error would really be a problem. Okay? A lot of thermodynamics problems are like that. Okay? So in thermodynamics, you kind of have to do these flash calculations, and you have to do them a lot of times. You need good accuracy. You don't always have time for good accuracy, so there's a balance always there between accuracy and time you have to compute. Excellent. So now, how about systems of ODEs? Actually, we can reformulate systems of ODEs into, or massage them into what we actually know how to solve. So here's an example. This is a standard system where I have things that depend on each other. So I'm computing 2 things, not just one. Okay? But they depend on each other. So I will have how, in this case, there's number of lions depends on what is the birth rate of lions, as well as how much food they have when they survive. The little ones that get. And whereas gazelles, they kind of depends on birth rate of gazelles and also how many lions are there to eat them. Okay? So we can actually formulate, and that's why they're coupled. So if I'm propagating things in time, I cannot propagate them separately. These things have to interact. So number of lions in time is basically birth rate of lions times number of lions times number of gazelles minus, well, they also die naturally. Lions die naturally. Gazelles are mostly eaten by lions. Okay? So unless we're in a zoo, but that's a different system. Okay? So in nature, this is a simple system. And you could do a lot of things that are coupled. Classical coupled thing in a much complicated way is pressure and velocity of a fluid are always coupled, and they affect each other in a nonlinear way. So you typically, at the same time, you have to solve for one, solve for the other, then let them interact, and then move on. Okay? And this is what's expressed here in these coupled equations in the system. So the way we actually formulate that, let's, in sort of some general case, say that I have 2 variables, y and z. They both depend on x, but they also depend on each other. Mathematically, dy dx is f1 over x and y and z. And dz dx is a function of x as well as y and z. Okay? Though I'm looking for y of x and z of x. Yes? Okay. I could proceed, just like, let's say that I'm solving this with Euler's method. I could proceed, so my yi plus 1 is yi plus, again, my slope now is given by f1, and current values of xi, yi, zi, times step h. I'm stepping forward in h. In x, I'm taking this step h, right? And zi plus 1 is my previous value of zi, and again, slope, because that's what slope is given by, okay? Just like in case of those lions and gazelles, times h. And then I'm going to update both of these and then move forward. So the next step, I'm going to take these newly computed yi plus 1 and zi plus 1 here, as well as xi plus 1, right? And that's going to play into how this f1 is changing with the new values and f2 is changing with the new values. So I'm going to solve for these simultaneously. Okay? So that's how we can solve for systems. I'm really just I'm looking for y and z at the same time. So I'm just doubling the work. Now, if this was Runge-Kutta method, there would be 4 lines for yi plus 1 and 4 lines or 5. So there will be a little more work, but it's still a straightforward application of whatever we had for solving just for one of them. Okay? It's just that it's not f of xy anymore, it's f of x, y, and z. And if I had more of them, well, by all means, of more of them. Yes? So I can basically just extrapolate how we're solving for one function of one variable to multiple functions of that same variable that possibly interact with each other. So this is how it would look like if you had Runge-Kutta. You would have a set of separate slopes for your f1 and separate slopes for f2. But with cut, copy, paste, and adapting the code that you already have, you could figure it out for a system. Yes? And slope, there's 4 slopes for both, function 1 and function 2, and then you would combine them the way we would combine them for Runge-Kutta method. So again, the actual method itself doesn't matter. I kind of solve for both at the same time and use the value of the others that I coupled with. Okay? So again, you could have not just 2, but you could solve for n things at the same time, if they're coupled, okay? And the main problem here is figuring out your typos in the code and solving it correctly, right? And straightening out what I call accounting, okay? And keeping things straight. And you have gotten a good taste of accounting in your computational project, okay? Conceptually, it was relatively simple, but then concepts to actual application and doing it correctly is not necessarily trivial. All right. Now, what about if I have, can you transform this problem into a system of ODEs? Y double prime of x plus 4y is equal to 0. And there are some hints written on the... So I have a second order ODE right now. And what I'm technically looking for at the same time is both for y and y prime. And both are function of x. So it's just like looking for those y of x and z of x. My z of x will become y prime of x, right? So if I actually say, my z of x is y prime of x. Everybody following? That's my first equation. Y prime of x equals to z is my first equation. My second equation is from here. So this is z prime of x plus 4y is equal to 0. Let me start writing. And I'm going to switch to this because I haven't rebooted my machine. so that means that it probably wouldn't work today. So let me just explain for the video. So the way we transform a higher order ODE into a system of ODEs that I just explained to you how to look for is by basically my y of x, I'm looking for my y of x, and all of the derivatives along the way, I'm going to give them a new name. Okay? So essentially my z of x is y prime of x, and that gives me one equation. And in this case, my second equation is then that z prime of x, which is double prime, y double prime of x, is equal to minus 4y. And those are two equations that I'm going to simultaneously solve for. I, of course, need initial conditions for both. Okay. Let me, this is basically solution for it, but I'm going to write it down, and you have those solution in the slides. So I'm going to switch to document. Okay. So my y double prime of x plus 4y of x is equal to 0, which is often just posed as this. Okay. And this is subject to initial conditions. Y of 0 is 0, and y prime of 0 is 1. So this is a higher order ODE than what we're used to solving, okay? So far we only solved first order ODE. This is second order ODE. How am I gonna change this to a system? I'm gonna change it by defining that my z of x is equal to y prime of x. Yes? So this is essentially equivalent saying that dy dx is equal to z, correct? My y double prime of x is effectively, using this definition, my z prime of x plus 4y is equal to 0. That means that my dz dx is equal to minus 4y. Does everybody see a system? I'm looking for y of x and z of x, both of them depend on x. And I have a slope of y and a slope of z, how they're changing with respect to x. And I could call this x, I could call it t, I could call it whatever I want to call it. That doesn't change. So this is what we're calling my f1 of x, y, and z. Right? It's a simple function, it's a z. It's still a function of x, y, and z. And this is what I'm calling f2 of x, y, and z. So let's first solve this just by one step. Let's just do Euler's method. Okay. And this is, I have initial conditions given at 0. Okay. Give me an h, step h. 0.5 to make it simple on paper. So let's say h is 0.5. Okay. Then my next x, so x0 is 0, x1 is, well, 0.5. My previous x plus h, right? What does Euler's method say? Y of x1, which is y of 0.5, is my y of x0 plus slope, which in Euler's method is a simple f1 of x0, y0, z0 times h, right? Euler's method always has that simplest slope you could possibly have. It's the same f you have here. Yeah? So what is that? Y of x0 is my y of 0. That's given in the problem. That's a 0. Plus, what is my f1 of x, y, z? Z. So what is z? So that's z0. What is z0? Z0 is z of x0, so that's y prime of 0. What is that given? It's given an initial value problem. What is it? 1. It has to be given, otherwise I can't solve the ODE. So z0 is 1 times h. So this is really 0 plus 1 times 0.5. It is 0.5. Yes? What is my z of x1 or z1? That is z of x0 plus f2 of x0, y0, z0 times h by Euler method. And that is equal to, what is z of x0? Z of 0. 1, that's given by the problem. Plus, what is f2 of x0, y0, z0? f2 is minus 4y. So it's minus 4 times y0 times h. What is y0? 0. So that's simple. This is 1. So this is my first step of this coupled problem. If I kept going further, now I would say y of x2 is y of x1 plus f1 of x1, y1, z1 times h. And this, in this problem, is just z1, which I have just computed in the previous step, yes? And I'm using it, otherwise it wouldn't be a coupled problem. And then my z of x2 is z of x2 plus f2 of x1, y1, z1, which is minus 4 times y1 times h. And I would keep going. If I were programming this, this is a very nice for loop. When do I stop? I didn't tell you in this problem. So I tell you compute y and z at, for instance, x is equal to 2. Then I would take this as many h's I needed to get to 2. Yes? And my solutions, y and z, I can then plot against x's on this 0 to interval. Yes? If the method was a little more complicated than Euler, then I would have these multiple slopes that I would compute for each of these f1 and f2 and then combine them into my final slope that I use.
How do you know which, like, where to use f1 and f2 in the formulas? It's like we just.
So whatever was f in the formulas for all of those methods for ODEs, now you use f1 and f2 separately.
But how do you know? Because you associate f1 with calculating y and f2 with calculating z. How do you know to do that?
So this is for y, and this is, so yes, f1 is for y and f2 is for z. I could have called it fy and fz, I guess.
I know, but how do you know that it goes like from
You program it separately. These are two different functions.
I know they're two different functions, but how do you know to associate two? Like we first calculated dy over dx.
Mm-hmm.
Oh, never mind.
Yeah.
Stupid.
Okay, no, it clicked in. That's good. Any other questions? That's the whole point about formulating questions. Without formulating questions, it cannot click in. Okay? All right. That is it for ODEs. I will now leave, and if you can, again, administer the surveys and